The purpose of this video is to match the operating principles of the pump with the circuit diagram to help resolve any issues in the future through better understanding of the pump. The pump featured in this video is used in most Dusen machinery. This will enable you to understand the actual operating principles of pumps and their controls more clearly. In brief, the pump is assembled directly with the engine, so when the engine rotates, the pump rotates along with it, causing suction, blue, and discharge, red, as shown above. The pump is largely divided into three groups. The front pump is directly connected to the engine, at the opposite end is the rear pump, finally, there is the pilot pump or gear pump. Their locations on the circuit diagram are as follows. The rear pump is driven by a coupling connected to the drive shaft. The pump featured in this video is used in most Dusen machinery. This will enable you to understand the actual operating principles of pumps and their controls more clearly. As the engine rotates, suction and discharge are performed by the rotary group within the pump. At the same time, the final discharge flow rate is determined by the regulator. The flow rate determined by the regulator determines the final angle of the swash plate using a feedback lever connected to the regulator and a servo piston. This angle ultimately determines the stroke distance within the cylinder block and piston. The larger the angle, the greater the stroke distance, thereby increasing the amount of discharge. Increasing and reducing the flow rate refers to the speed of the actuator, cylinder or motor. This is a picture of an actual valve plate. It has a special shape. The valve plate is always fixed in place while the rotary group performs strokes. As shown in the picture, there are two grooves on the valve plate. During the suction and discharge of hydraulic oil, the valve plate is always fixed in place and the cylinder block is always rotating, causing numerous shocks during suction and discharge. The grooves function to facilitate suction and discharge by absorbing shocks during pump suction and discharge. Just as the sizes of the flow paths in the inlet and outlet differ, the grooves for suction and discharge also are different in depth. The red dots in the picture are holes for lubrication and cooling. If these are plugged, all of the parts inside the pump will be damaged. This is a spring known as a compensator or compensation spool. There are actually two springs, an inner spring and an outer spring, but only one is shown on the circuit diagram. This is known as a compensation spool or compensator. The compensation spool is composed of 3 chambers. This is a lever connected to the compensation spool. This is known as a spool. This is known as a spool spring. Every spring has its own spring constant against the hydraulic pressure at its part. When no pressure is applied, springs are returned to their original position by the given constant. This is a lever on a Nagaikin piston. This is a Nagaikin piston. This is a Nagaikin piston spring. This is a feedback lever. The final signal determined by these 2 small levers is transmitted to a part at the bottom. This is a servo piston, which is connected to the swash plate at the bottom and contributes directly to adjusting the flow rate. It is moved by the feedback lever shown above. This part connects the compensation spool and the spool. The compensation spool serves to control the pressure within the hydraulic system. Pressure is controlled by reducing the flow rate as the operating pressure increases. This is known as a PDQ curve. The lines on the graph varies depending on the pump specifications. As shown on the graph, the more the pressure on the bar at the bottom increases, the lower the flow rate in the left-hand bar becomes. This is the Nagaikin piston opposite the compensation spool. It is also connected to the spool with a lever. The Nagaikin piston, a kind of switch for the hydraulic system, is like a signal capable of controlling the pump swash plate angle first. Altogether, the part you see now is the compensation spool, located at the top, and on the opposite side is the Nagaikin piston. The compensator and Nagaikin piston have a spool between them and are connected by a lever. The spool in the middle is connected to the servo piston at the bottom, while the servo piston is connected to the swash plate, which determines the swivel angle. The compensator consists of 3 chambers. The red part shown in the video receives pressure from the corresponding pump, while the blue part always receives pressure from the opposite pump. Before explaining the 3rd chamber, we will describe the concept of pressure control as follows. The excavator that uses the pump shown is about to begin digging. Soon, it will be controlled by the regulator inside. This is for your information. Feedback lever connected with spool is always connected with servo piston.
That's good.
The reason that the servo piston moves from the large chamber to the small chamber at the same pressure is because the former has a larger area, although their pressures are the same. Once the system operating pressure has built up as a result of digging, the flow no longer needs to be swift. Thus, the angle of the swash plate decreases to reduce the flow rate. Remaining in this state with an increased flow rate while the pressure is high load, can severely damage the engine, as well as having an impact on fuel consumption and durability. As shown on the screen, causing the flow rate to decrease when the pressure rises above 120 bar is known as pressure control. We refer to the main part which creates a signal for flow control as a negation valve or a foot relief valve. Located at the very top of the control valve, it is divided into two signal lines on the front and rear of the main pump, which of each delivers a signal to its regulator. Hydraulic oil discharged from the front and rear pump enters the control valve. When not in motion, pressure is delivered through the flow path in the control valve. We refer to this large flow path for hydraulic oil in the control valve as the center bypass line, which of each delivers a signal to its regulator. Now, let's have a look at how this actually works in the foot relief valve. Oil discharged from the main pump is supplied to the foot relief valve through the center bypass line. At idle, the low RPM results in a small discharge volume and thus creates a low pressure. The negation pressure is around 20 to 25 bar during idling. The circuit of the yellow part includes an orifice and a relief valve. As shown on the screen, increasing the RPM to its maximum opens the relief valve, while the negation pressure increases to around 40 bar, the pressure set with the spring in the foot relief valve. The negation pressure is designed not to allow the maximum pressure to exceed the set pressure with the set value of the foot relief valve. Thus, the negation pressure is supplied to the negation piston in the main pump regulator, which then functions as a signal. EG is running in no operation condition. Normally negation pressure 25 bar to 35 bar depending on RPM. Negation piston is moved by negation pressure. Spool is moved by negation piston feedback lever. Spool is moved and oil path open. Oil goes to large chamber of servo piston. Finally, pump oil discharge will decrease. Begin operation. Bypass line is cut by spool in MCV. Negation piston and spool are returned by low negation pressure. Large chamber oil goes to pump casing as lubricant of pump inner parts. There is no pressure inside of large chamber. Space of small chamber is smaller than large chamber. Also there are still pressure inside and then servo piston will be pushed to large chamber side. Oil discharge will increase. Now, machine is power mode operation. EPPR valve reducing pressure from 40 bar to 0 to 16 bar. It should be changed depending on RPM drop rate. EPOS deliver 200 mA signal to EPPR valve at this time. Now, machine is standard mode operation. EPPR valve reducing pressure from 40 bar to 8 to 28 bar. It should be changed depending on RPM drop rate. EPOS deliver 300 mA signal to EPPR valve at this time. Now, machine is standard mode operation. EPPR valve reducing pressure from 40 bar to 32 bar. It should be changed depending on RPM drop rate. EPOS delivering 700 mA signal to EPPR valve at this time. As you can see in the table above, the larger the milliamp value delivered to the EPPR valve by the EPOS, the more the secondary pressure increases.
That's good.
The 40 bar pressure generated in the pilot pump is delivered to the EPPR valve. After receiving the milliamp current from the EPOS, the EPPR valve opens the valve by the amount of milliamp received. Then, it decompresses the 40 bar pressure to create secondary pressure. Thus formed, the secondary pressure is delivered to both ends of the compensator in the pump regulator. When the machine is running, the secondary pressure serves to optimize the performance of the machine along with the system pressure. The graph above shows the secondary pressure, the operating mode of the machine, and the system pressure in each mode. As you see, the secondary pressure varies by mode.
That's good.
Informed of the RPM and pump pressure sensor value, the EPOS precisely controls the current, milliamp, by calculating the pressure and drop in engine RPM which occur while the machine is operating. Oil does not pressurize between the gears but along the outer side of them. Since the oil passage is formed along the outer side of the gears, hydraulic oil flows through this, rather than between them. The pressure from the pilot pump is constant, not variable. Hence, if the pressure exceeds the said level of 40 bar, relief is conducted using the relief valve as shown above.